exercise 13, event by event solution. We now build this exercise with a conditional function on every single snowstorm event being generated individually. On the previous exercise, we multiplied the number of snowstorms per year times the average number of days of snowstorms in order to obtain the total number of snowstorm days per year. By this approach, the mean number of snowstorms per year is correctly calculated, but the shape and length of the tails is not necessarily the correct one. Consider the following example. The Poisson frequency distribution has a lambda, that is a mean of 6.5 snowstorms per year. On such a distribution, imagine a certain iteration at which 10 or more snowstorms can be simulated. This would typify a relatively snowy or harsh winter. Theoretically, there's a 12.3% chance that such an outcome can be generated. Now, imagine that at any one of these sample iterations for 10 or more snowstorms, it happens also that the PERT duration of the snowstorm is of 4 days or more, even though the mode is just 1.5 days per snowstorm. This event is also possible, since it might theoretically occur on 3.7% of the samples or iterations being simulated. By conditional probability, multiplying 12.3% times 3.7% roughly equals 0.5%. This means that if we were to simulate some 10,000 iterations, approximately some 50 iterations would generate an outcome with a minimum of 10 times 4, that is equal to 40 snowstorm days per year. This is highly unlikely. It intuitively makes sense to think that on such an extreme iterations of 10 snowstorms, not necessarily all of them will have an extreme duration of 4 days of snowstorm. Some will have less than the most likely scenario of 1.5 days, some more than that. However, since each one of the 10 snowstorms has within it several days of duration embedded within it, we could say that this is a case on which the probable days duration of each snowstorm is an embedded distribution within another probabilistic distribution for the number of snowstorms per year. This is what mathematicians call a convolution. Imagine variation of snowstorm days, the PERT impact function, embedded within the variation of the frequency of snowstorms, the Poisson frequency function. If the convolution is not performed correctly, for example by using a simple multiplication, the effect on the tails of the compounded or convoluted distribution might be overestimated. The next exercise creates this same effect of convolution by adding one by one each one of the snowstorms and allows understanding the difference between these two approaches. On cell B110, insert the probable occurrence of a snowstorm contingent on the Poisson frequency distribution. This conditional function allows an individual snowstorm to be generated, a 1, only if the number of snowstorms on any given simulated year is less than or equal to the iterated sample being drawn at the Poisson on cell B101. Insert the following function. Equals if open parenthesis A110 is less than or equal to $B $101, 1, 0. Copy and paste down this cell for the range B110 through B129, allowing to as much as 20 probable events per year. On cell C110, we model the duration of snowstorm days per snowstorm, provided that such a snowstorm occurs during a certain sample year. Insert the following formula. Equals B110 times risk PERT, open parenthesis, $B $103, $B $104, $B $105, close parenthesis. Copy it and paste it down for the same 20 events range. On cell C108, Calculate the sum of all snowstorm days individually generated with the formula equals sum, open parenthesis, C110 through C129, close parenthesis. Declare cell C108 an output cell. It should read like this: equals risk output, open parenthesis, quotes, event model, risk composed event by event, quotes, close parenthesis, plus sum, open parenthesis, C110 through C129, close parenthesis. Turn on the random/static standard recall button in at risk and recalculate several different iterations keying F9 to watch how the list of snowstorms creates different scenarios where each one of them has a different duration. When we simply multiply frequency times impact, we are not allowing for each event to have a different duration. By individually creating variation for each event, given that the number of events is also stochastic in nature, we have manually created a numerically generated convoluted model. Now, run 10,000 iterations on your simulation. Make sure your demo mode is on in order to be able to see what happens during this simulation run on top of this conditional range. You will see the range of snowstorms shrinking and expanding at every single iteration that composes your simulation. The important concept here to remember is that there is a simultaneous double variation going on here for every single iteration. At every single iteration level, not only does the number of snowstorms change, but also every single duration of each one of them changes. It is not that the duration of all snowstorms remains equal for every single iterated number of snowstorms per year. Maintaining the same duration for all snowstorms at the iteration level is equivalent to the previous exercise on which we simply multiplied frequency times duration. Convolution is something else. It goes beyond multiplication. It is not simply multiply number of snowstorms fixed times your duration. It goes by adding snowstorms of different durations, each the variable number of times given by the frequency of the iteration. Remember, you can always turn off your demo mode, both buttons that update the Excel display and the chart display. Once the simulation has finished, compare the two outputs generated. Go to Results Summary window within the Export button and drag out the first output graph from cell B99. Overlay the two distribution functions from cell B99 and C108. By clicking on the Summary window and dragging out respectively these two outputs, you can compare the two overlaid graphs. The graph should look like the following. Observe that the mean is essentially the same. Its minor difference stems out of the very random nature of the simulation process. But this difference converges to zero by increasing the number of iterations. The major difference can be seen on the tail beyond 30 days. While the first multiplicative approach rendered a 5% probability of a year with more than 30 days of snowstorm, the convoluted distribution only generates such an outcome on 0.7% of the time. In other words, the first approach places more than 30 days occurring approximately every 20 years, while in reality, such an outcome only occurs once every 125 years. This is an extended tail over 6 times larger. On the other hand, normal, between quotes, years of less than 20 snowstorm days per year may happen on 86% of the time, as opposed to only 80% of the time, calculated with the first multiplicative approach.